Dear students, that day we have discussed about gravitation. That it is the gravitation is defined as the force of attraction between any two bodies in the universe, and this force of gravitation depends upon the mass of the two bodies and distance between them, which is calculated by gravitational force is calculated by G m1 into m2 by d square, where m1 and m2 represents the masses of the two bodies and d represents the distance between their centers. Then in that condition, gravitational force is calculated by G m1 into m2 by d square. If let m1 equal to x kg and m2 equal to y kg, in this condition, if z is the distance between them, z meter is the distance between them, in this condition, if g represents the universal gravitational constant, then then we can write F equal to G into X into Y by Z square. So this is the formula, this is the representation. If masses are X kg and Y kg, and Z is the distance between their centers. Now, today I am going to explain you about acceleration due to gravity and universal gravitational constant. Acceleration due to gravity means the acceleration produced in a falling body, freely falling body due to gravity. Value of acceleration due to gravity. Value of acceleration due to gravity on the surface of the earth is equal to, it is taken to be 9.8 meter per square second, average value, and its value varies from place to place. G at polar region of the earth, this is taken to be 9.83 meter per square second. G at equator, it is taken to be 9.78 meter per square second. G on the moon surface, it is 1.6 meter per square second. And on the different planet, value of acceleration due to gravity is different. Acceleration due to gravity, it is vector quantity. Acceleration due to gravity is a vector quantity. Its unit is taken meter per square second, and value of acceleration due to gravity, it is calculated by G equal to Gm by R square, where M represents the mass of the earth or planet. This is a small m is the mass of the object kept on the planet, and R represents the radius of that planet. In this condition, value of acceleration due to gravity is calculated by Gm by R square. Here, capital G represents universal gravitational constant, where the value of capital G, as we are obviously using 6.67 into K power minus 11 Newton meter square or kg square. Acceleration due to gravity. There are some of the differences between a small g and capital G. A small g. Differences between a small g and capital G. A small g and capital G. This represents acceleration due to gravity. It represents acceleration due to gravity, and it represents universal gravitational constant. universal gravitational constant. Similarly, its unit is meter per square second and unit of capital G is Newton meter per square second. Its unit is Newton meter square per kg square. Similarly, 3 number. Unit here average value. Average value is 9.8 meter per square second on the earth. And value of capital G equal to 6.67 into 10 power minus 11 Newton meter square per kilogram square. This is accessible to gravity, which is vector quantity, and this is a scalar quantity. It is a scalar quantity. In this way, there are few differences between accessible to gravity and universal gravitational constant. Here, this accessible to gravity is denoted by small g and universal gravitational constant is denoted by capital G. Value of G, actually the value of accessible to gravity, its value varies from place to place. Varies from place to place on the earth, but its value remains constant. Value remains constant all over the universe. All over the universe. In this way, we can differentiate between accessible to gravity and universal gravitational constants. Now, we will discuss about the variation of small g and the variation of acceleration due to gravity. How value of acceleration due to gravity varies from place to place. Variation of acceleration due to gravity. Variation of acceleration due to gravity. As we know that value of acceleration due to gravity varies from place to place. There are few factors of variation of acceleration due to gravity, just like due to the shape of the earth, due to the height above the earth, and due to the depth below the earth. There is one more factor due to the rotation of the earth, and the last factor is not included in class 10. Here we study about variation of acceleration due to gravity. Variation of G due to the shape of the earth. Before this, I am going to prove. We will prove that acceleration due to gravity depends upon the radius of the earth, and the formula of acceleration due to gravity is small g equal to gm by r square. And in the same, we will prove that g is inversely proportional to r square, where r represents the radius of the earth or the planets. Acceleration due to gravity is independent on the mass of the earth, mass of the object. It depends upon the mass of the earth or planet or satellite and radius of the earth. Here, to prove this, we consider a heavenly body. Suppose this is earth of mass m, O is the center, and r represents the radius of this planet, where a small object is kept at these points. We consider this. Here, F is the gravitational force of attraction between them. We explain the same thing. Let a small object of mass m is kept on the surface of the earth. This object. Its mass is small m and the radius of the earth is capital R. Let R is the radius of the earth. F is the force of attraction between them. We have explained this, and then by Newton's law of gravitation, you can write the force of attraction between them is given by F is equal to G into M by R square. So we can write here G M by R square. As we know that gravitational force is equal to G into M1 into M2 by D square. Here the distance between them is R, radius, equal to the radius of the earth. So it is equation first. Similarly, if we take the gravitational, here is the gravitational force between them. Now, by Newton's second law of motion, you can write F is equal to M into G. As you know, F equal to ma. Here, G represents the acceleration due to gravity. These two forces being equating 1 and 2, we get Gm into m2 or Gmm by R square equal to mg. So we can write mg equal to Gmm by R square. And cancelling this, small m cancels from left side and right side, and therefore Gm by R square. This is the value of acceleration due to gravity. Hence, we can prove that acceleration due to gravity is equal to Gm by R square. Now, since G and M are constants, therefore we can write. So we can write from equation 3, G is inversely proportional to R square. This relation gives that acceleration due to gravity depends upon the radius of the Earth or planet. It is inversely proportional, means to say that if radius of the Earth changes, radius of the planet or Earth or satellite changes, acceleration due to gravity also changes from place to place, and it is inversely proportional to the square of the distance. And one point is to be noted that our Earth is not exactly spherical. The shape of the Earth is in this way. We can say that it is flattened at the poles and burned at the equator. So it has two radii. One radius, this is equatorial region. So its radius is RE, and here is RP. This represents the polar radius. So this radius represents the polar radius, and this represents the equatorial radius. Since RE, as according to the figure, equatorial radius is bigger than the polar radius RP, so we can write GP is greater than GE, where GP represents the acceleration due to gravity at poles, and GE represents the acceleration due to gravity at equator. Now, One point is to be noted that accessible to gravity at polar region of the Earth is 9.83 meter per square second. Similarly, accessible to gravity at the equatorial region is 9.78 meter per square second. On average, the value of accessible to gravity is taken to be G on the Earth. G, this is taken as it is equal to 9.8 meter per square second. So, from the given figure, we can see that accessible to gravity varies from place to place on the Earth. It is due to the shape of the Earth. First reason, that due to the shape of the Earth, accessible to gravity, value of accessible to gravity varies from place to place due to the shape of the Earth. As you know that our Earth is like orange shape. It is not exactly a spherical like a ball. It is flattened at the poles and at the equatorial area it is bald. So there are two radii of the Earth. One is polar radius and other is equatorial radius. And since we know that accessible to gravity varies inversely proportional to the square of the distance, square of the radius. So here from the figure, RE means equatorial radius is bigger than the polar radius. So we can write GP is greater than GE. Since equatorial radius is bigger than the polar radius, so accessible to gravity at polar region is more than the accessible to gravity at the equatorial region, and value of accessible to gravity are given at polar equator. Value of accessible to gravity on the Earth. To calculate the value of accessible to gravity, we use this formula G equal to Gm by R square. By using this formula, we can find the value of accessible to gravity on the Earth, just like mass of Earth. This is M equal to 6 into 10 power 24 kg. 6 into 10 power 24 kg is the mass of the Earth. Radius of Earth R, it is equal to 6400 kilometer. Is equal to 6.4 into 10 power 6 meter. We have to express that into meter into SI system. Gravitational constant, its value is 6.67 into 10 power minus 11 Newton meter square per kg square. So, acceleration due to gravity can be calculated by the formula acceleration due to gravity small g equal to what? We have a small g equal to Gm by R square. Using the same formula, you put the value of the given terms 6.67 10 power minus 11. Here is M is the mass of the Earth. So we take 6 into 10 power 24. 6 into 10 power 24 by 6.4 into 10 power 6. It's a square. This on calculation gives 9.8 meter per square second. This is the value of accessible to gravity on the surface of the Earth. Then, now, variation of accessible to gravity due to height above the Earth. For this, just I am going to erase it. Now, the second is the variation of accessible to gravity due to height above the Earth. How accessible to gravity varies above the Earth? When the height increases, accessible to gravity go on decreasing. To prove this, we take Earth as a spherical object. This is the mass of the Earth. This represents the radius of the Earth. O is the center. An object is kept at suppose point A. The mass of the object is small m. This object is shifted to point B up to height h above the height. This is the height f from A to B. Here AB, this distance is taken to be yes. Therefore, from O to B, it is equal to R plus S. R plus S. Accessible to gravity at B is suppose G prime, and accessible to gravity at A, it is taken G. Here, I'll prove that accessible to gravity G prime will be less than G. Let's a small object of mass m is kept on the surface of the earth. Surface of the earth of mass m and radius r. This object is shifted from A to B to a height h above the ground. Let G and G prime are the acceleration due to gravity. Acceleration due to gravity at A and B respectively. A and B respectively. क्रमिक रूपमा यहाँ acceleration due to gravity small g छ, यहाँ capital small g prime छ B point मा. Now at A we can use G equal to Gm by R square. As according to the previous formula, acceleration due to gravity from this point A is G equal to Gm by R square. Using the same formula, we can write and at B, at point B, you can write G prime is the acceleration due to gravity. Then G prime equal to Gm by G prime is for B point, so total distance will be R plus X from O to B. R plus X is whole square. And dividing equation 1 by 2, we get equation 1 by 2. Or it is better to write 2 by 1, we will get G prime by G. G prime by G, this is equal to Gm by R plus F, its whole square, by Gm by R square. This term is equal to Gm by R plus F, the whole square, into R square by Gm. So G and M cancels, and it is equal to R by R plus F, its whole square, R by R plus F, the whole square. Here, G prime by G equal to this much. Therefore, we can write G prime equal to G cross multiply G into R by R plus F the whole square. Here, one point is to be noted that R plus X, this term is bigger than R, so R plus X. R plus X, this term is less than 1. Then on calculation, this term R by R plus X, this term is less than 1. Therefore, we can write G prime is less than G. G prime is less than G. This concludes that accessible to gravity decreases above the height, and value of accessible to gravity at height, yes, above the earth is calculated by this formula, equation number 4. And In the given calculation, we have studied that acceleration due to gravity decreases as the altitude increases. With the increase in height, acceleration due to gravity decreases above the earth, and weight of an object is equal to m into g. As acceleration due to gravity varies from place to place, since acceleration due to gravity varies from place to place and mass is a constant, so we can say that weight depends upon acceleration due to gravity. Just like weight of an object is less on the top of Mount Everest than on the surface of the earth due to the same variation of acceleration due to gravity. As we know that height increases, acceleration due to gravity decreases. Here, a small g or g prime equal to gm by r plus hb whole square. In equation 2 we have taken, since g and m are constant, so g prime can be taken is inversely proportional to r plus hb whole square. Means to say that with the increase in height, acceleration due to gravity decreases. It is therefore on the surface of the earth, value of acceleration due to gravity is more than that on the height above the earth, or above the surface of the earth. Now, you may be asked in the given topic that value of acceleration due to gravity is less on the top of mountain than on the surface of the earth. Why? It is due to the same reason that as the height increases, acceleration due to gravity decreases. As the altitude increases, acceleration due to gravity decreases. It is therefore on the top of mountain, due to more height, value of g is less, and it is therefore weight of an object is also less on the top of mountain. Now, related numerical is here to calculate the acceleration due to gravity on the top of mountain. Just like if mass of the earth is 6 into 10 power 24 kg and its radius is 6400 kilometer, find the value of acceleration due to gravity. Value of acceleration due to gravity on the top of Mount Everest. On the top of Mount Everest, you have to calculate the value of acceleration due to gravity on the top of Mount Everest. Value of a small g on the surface of the earth is given. Surface of the earth, it is given, this is 9.8 meter per square second. We have to use this here. For a solution, first we find out given data that mass of the earth is here. Mass of the earth, it is given 6 into 10 power 24 kg. Radius of the earth, this is capital R, equal to 6400 kilometer. This is equal to 6.4 into 10 power 6 meter, and a small g, acceleration due to gravity. This is acceleration due to gravity on earth. This value is given, it is equal to 9.8 meter per square second, and we have to calculate value of g, acceleration due to gravity. Gravity on the Mount Everest. This is g prime, and it is equal to watts. G prime is equal to watts. Here, in the given data, height of Mount Everest must be given. Height of Mount Everest is 8848 meter from the earth. This point is missing. Here you use the height of Mount Everest as according to the given data. 8848 meter. Here G prime equal to Gm by R plus H is whole square. Here you can use two formulas. Small g equal to Gm by R plus H the whole square and G prime equal to G into R by R plus H its whole square. Both formula can be used, but according to the given data, here accessibility to gravity is given. Therefore, you can use this formula or this also. Here, G is universal gravitational constant 6.67 into 10 power minus 11 into M 6 into 10 power 24 by R 6.4 into 10 power 6 plus 8848 is whole square. This calculation, by calculating this, it comes 9.77 meter per square second.